Welcome back to another deep dive. Today we are going to get into something that is, honestly, it is inescapable right now.
It really is the word of the moment.
If you open your news feed, you talk to your tech friends, and there is just one word that keeps coming up over and over.
Reasoning, the absolute holy grail of AI right now.
Exactly. Reasoning. We are not just talking about standard chatbots anymore. We have definitively moved past the era of, asking a model to suggest a dinner recipe or write a limerick about your cat.
We're in a whole new paradigm.
Yeah, now we have OpenAI's O1 and O3 series, we have DeepSeek R1, we have Claude 3.7 Sonnet, and the marketing around these things has shifted completely. They are not being sold as large language models anymore. LLMs are old news.
Right, now they are large reasoning models, LRMs.
LRMs, and that is a pivotal shift in the promise they're making to us.
It is fundamentally different. The pitch now is that these models do not just blurt out the next statistically likely word. They supposedly pause, they think. They plan out a trajectory and double-check their work before they hand you an answer.
Which, to be fair, sounds incredible. I mean, it sounds like we are finally getting that sci-fi AI that can actually solve hard problems rather than just mimicking human speech patterns.
It is a very seductive idea.
It is, and I have used some of these thinking models. And just watching that little thinking bar pulse while it works, it really feels like there is a brain in there churning away.
It is a brilliant UI feature, honestly. It buys the system time while building anticipation for the user. You feel like you are waiting on a genius to finish their calculations.
But there is always But on this show, we have a brand new research paper to dig into today. It is from a team at Apple led by Shoje and colleagues, and it suggests we might need to pump the brakes a little bit on this whole reasoning narrative.
A significant amount of pumping, I would say.
Yeah. The paper is titled The Illusion of Thinking.
Which is not exactly a subtle title.
No, it is pretty aggressive, and the core question they ask is the exact mystery we are going to unravel in this deep dive. Do these models actually possess generalizable problem-solving skills, like true reasoning, or is this entire thinking process just a very sophisticated, very expensive illusion based on pattern matching?
That is the defining question of the year for AI. And what this Apple team found is fascinating because it directly challenges the narrative we are hearing from the major AI labs.
Right.
They found that when problems get really, really hard, when they push past a certain complexity threshold, these models do not behave the way a thinking entity should behave.
Okay, let's set the stakes for everyone before we give away the ending. The basic human assumption is this. If I give a smart person or a smart machine a harder problem, they are going to think harder about it.
Right. They will take more time, they will use more brain power, effort scales with difficulty.
But the data in this paper shows something completely different, doesn't it?
It shows the exact opposite. When the going gets really tough, the AI just collapses. And in some cases, it actually gets lazy. It literally gives up.
That is a wild claim to make about the most advanced tech on the planet. So our mission today is to look under the hood of these thinking traces.
We are going to get into the weeds.
We are going to figure out why the standard math test that everyone relies on might actually be lying to us. We will see what happens when you force a super intelligent AI to play simple logic games where it absolutely cannot cheat.
And we will look at exactly how their internal thought processes break down.
Yes. So let's start with the status quo. To understand why this Apple paper is making such huge waves, we have to talk about how we usually grade these models. Because whenever a new model drops, say, DeepSeek R1, we inevitably see a massive chart on Twitter.
Oh, the benchmark charts.
Right. And that chart usually says the model got a perfect or near perfect score on something called AIM or Math 500.
Right. And those are considered the gold standards right now. AIM stands for the American Invitational Mathematics Examination.
And this is not basic algebra.
Not at all. It is a high-level math competition for the absolute best high school math students in the United States. It requires intense creative problem solving. You cannot just plug numbers into a standard formula to pass the A. And recently we have seen these new reasoning models achieving incredible, sometimes near-perfect scores on these benchmarks.
And naturally, when you or I look at that, we think, wow, I definitely could not pass the AIM. So if the AI can crush high school competition math, it must be brilliant. It must actually be reasoning.
That is the intuition. But there is a massive structural problem lurking in the background of all these benchmarks. And it is a problem the AI industry is finding harder and harder to ignore.
Contamination.
Exactly. Data contamination.
When I hear contamination, my mind goes to a crime scene or a biohazard lab. But what does it mean for an AI?
Think about how these models are built. They're trained on essentially the entire internet. They have scraped every textbook, every exam repository, every GitHub repo, and every discussion forum like Reddit or MathStack Exchange.
Okay, I see where this is going. If the AIME test from 2023 was posted online.
Then the model has read it, probably thousands of times. It has seen the question, it has seen the debates about the question, and crucially, it has seen the step-by-step solution.
But wait, let me play devil's advocate here for a second. Humans study past exams to learn. If I am prepping for a huge test, I am going to take practice tests. I look at the answers to understand the logic. Why is it considered cheating or contamination when an AI does it? Isn't that just learning?
It is a great question, but there is a crucial distinction in how learning happens. When a human studies a past exam, they are ideally, anyway, trying to internalize the underlying principles.
Right.
If I learn how to solve a complex geometry problem on a practice test, I can then go and solve a completely different geometry problem on the real test.
Yeah.
I acquired the skill.
You learn the mechanics of geometry.
Exactly. But for a large language model, learning often looks a lot more like retrieval. It's not necessarily deriving the answer from first principles. It is recognizing the string of text that makes up the question and essentially retrieving the solution string that it saw during its training phase.
So it is the difference between knowing how to bake a cake because you actually understand the chemistry of flour and baking powder.
Versus just memorizing a recipe card word for word.
Got it. So if I take away the recipe card, or if I ask you to bake a cake at a higher altitude where the physics changed, the memorizer is totally lost.
Precisely. And the Apple researchers proved this contamination issue in a really elegant way. They looked at the performance gap between the AM exam from 2024 and the brand new one from 2025.
Okay, so just a 1-year difference in the tests.
Right. Now, typically these exams stay relatively consistent in difficulty year over year. In fact, if you look at how human students performed, the 2025 exam actually seemed slightly easier. The human students scored higher on average.
Okay, so humans found the new test easier.
Yes, but the AI models, their performance dropped significantly on the 2025 test compared to their scores on the 2024 test.
Oh, wow. Wait, if the test is objectively easier for humans, the AI should definitely do better. Unless
it simply had not seen the 2025 test yet.
Right.
The 2024 test has been out for a while. It has been endlessly discussed online, which means it is in the training data. The 2025 test is fresh. The models could not cheat via retrieval because the answer key simply was not in their memory banks yet.
That is a smoking gun, isn't it? It strongly suggests that the 90% accuracy we see plastered all over marketing materials is really just 90% memorization.
In many cases, it is. It suggests that a massive amount of what we are calling reasoning is actually just very advanced, very fuzzy pattern matching. And that is exactly why the Apple team said, okay, we need an entirely new way to evaluate these systems.
We need a test they cannot possibly have memorized.
Right. We need to completely break the contamination loop.
And that brings us to the core of their methodology. They ditched the math tests entirely and went for controllable logic puzzles.
Yes. They used 4 specific types of puzzles for this paper: the Tower of Hanoi, checker jumping, river crossing, and block swirled.
I feel like I played half of these on a dusty computer in my middle school library.
They are absolute classics. But the key here isn't the game itself. The key is that these are algorithmic tasks. You can generate a completely fresh, unique version of the puzzle on the fly.
So the exact answer is not sitting on a web page somewhere waiting to be scraped.
Exactly. Take the Tower of Hanoi, for instance. You have 3 pegs and a stack of different sized discs on one peg. You have to move the entire stack to another peg. But the golden rule is you can never put a larger disc on top of a smaller disc.
Right. Very simple rules.
Very simple. But here is the magic of using it for an AI test. The researchers can turn a complexity dial. They can ask the model to solve it for just 3 discs, which is easy. It only takes 7 moves. Or they can dial it up and ask for 20 discs.
Which takes a massive amount of moves.
Millions of moves.
So they can precisely stress test the thinking capabilities. They can gradually increase the pressure and see exactly where the model's brain breaks.
Exactly. They did the same thing with the other games. Checker jumping, where you have to swap red and blue checkers on a one-dimensional line. River crossing, which is that classic logic riddle you have probably heard.
Like the farmer with the wolf, the goat, and the cabbage, where if I leave the wolf alone with the wolf eats the goat.
Yes, that exact type of constraint satisfaction puzzle. You have to get everyone across without violating the conflict rules.
Right.
And finally, block swirl, which is just about rearranging stacks of blocks into a very specific goal configuration.
So just to summarize for you listening, why do these simple games matter more than a high school math test?
There are three main reasons. Number one is controllability. Because they can dial the difficulty from a 2 up to a 10, they can perfectly measure how performance changes as the problem gets harder. Number two is no contamination. Like we said, these specific on-the-fly puzzle instances do not exist on the internet.
They have to figure it out live.
Right. And number three, which is crucial, is trace visibility.
Trace visibility, meaning we can actually see their scratch pad.
Yes, because these are supposedly reasoning models. They output their internal monologue. They output thinking tokens. So we can actually watch the AI write out, okay, first I will move disk 1 to peg 2. Wait, no, that will block disk 2. I should move it to peg 3 instead.
We can see the actual process, not just the final answer.
Exactly. And when the researchers ran these stress tests, looking closely at models like DeepSeek R1, Claude 3.7 Sonnet, and OpenAI's O3 Mini, they discovered something they organized into the three regimes of AI performance.
The three regimes. That sounds very academic. Let's break these regimes down. What is regime 1?
Regime 1 is low complexity, the easy stuff. 3 disks on the tower, a simple river crossing with just the basic characters. And here is the very first surprise they found. The fancy, highly marketed, expensive thinking models, they are not actually the best choice here.
Wait, really? You would think the super genius reasoning model would completely crush the easy test.
Well, it solves it, sure. But the standard non-thinking models like your regular Claude Sonnet without the thinking mode turned on, or DeepSeek V3, they solve it just as accurately, but they do it much faster and for a fraction of the compute cost.
So using O1 or an LRM for a simple task is just overkill.
It is worse than overkill. It is highly inefficient. The researchers highlighted a behavior they call the overthinking phenomenon.
Overthinking. I think we all know a little something about that.
Right. Imagine you ask a brilliant theoretical physicist to make you a peanut butter sandwich. A normal person just grabs the bread and makes the sandwich. The physicist starts calculating the sheer stress of the peanut butter and the optimal spatial distribution of the jelly.
And 20 minutes later, you are still standing in the kitchen starving.
Exactly. When the expert analysis team looked at the traces, they saw that on easy tasks, these reasoning models actually find the right answer almost immediately. The correct solution is right there in the first few tokens of thought. But then
They keep going.
they just keep talking to themselves. They keep generating thought tokens. They start second guessing. They will write, wait, is this right? Let me verify. What if I move this other disk first? They go down entirely unnecessary rabbit holes, exploring incorrect paths long after they already solved it.
Oh man, I relate to that so deeply. It is like when you write the correct answer on a multiple choice test and then you stare at it for 10 minutes and convince yourself it must be wrong because it felt too easy. So you erase it and write the wrong answer.
It is a very human flaw, isn't it? But for an AI, it is a massive waste of computational resources. It proves that the thinking process is not inherently efficient. The model does not have a reliable internal gauge to know when to stop and just say, I got this.
Okay, so the takeaway for regime 1 is, for easy stuff, stick to the standard models, save your API credits. But what about regime 2?
Regime 2 is medium complexity. This is the sweet spot. And to be fair to the labs, this is where the marketing actually aligns with reality. As the puzzle gets a bit harder and requires more steps and more planning, the standard non-thinking models begin to fail. They lose track of the board state.
They just cannot hold all those variables in their context window at once without a scratch pad.
Right. But the reasoning models shine beautifully here. That thinking process allows them to explore a path, hit a dead end, recognize that it is a dead end, backtrack, and try a completely different approach.
So the self-correction mechanism actually works in this zone.
It works incredibly well in this medium range. The traces explicitly show them making mistakes, catching those mistakes, and fixing them. This is the moment where you look at the screen and think, wow, we really have achieved reasoning.
But I know there is a regime 3 coming, and regime 3 sounds ominous.
Regime 3 is high complexity, and yes, it is the collapse.
Define collapse for me. Are we talking about a gradual dip in performance?
No. We are talking about accuracy dropping to 0. Not 50%, not 20%, 0.
0%, even for the absolute best models on the market.
Across the board. When the problem passes a certain complexity threshold, say, a certain number of disks in the Tower of Hanoi, or a certain number of blocks to rearrange the models, simply cannot solve the puzzle.
But why? If they can solve the medium puzzle perfectly and the rules of the game are exactly the same, What changes?
This is the critical insight of the entire paper. It suggests that they never actually learned the algorithm.
What do you mean by that?
Think about how you or I would learn the Tower of Hanoi. Once you figure out the trick, you learn the recursive algorithm. Move n-1 disks to the spare peg, move the biggest disk to the target peg, then move the n-1 stack back on top of it.
Right. Once you know that underlying rule, it doesn't matter how many disks there are.
Exactly. You can solve it for 3 disks, 10 disks, or 100 disks. It just takes more time and patience. The logic never changes.
So the fact that the AI fails completely at high complexity proves it did not actually learn that general rule.
Right. It learned patterns of moves that happened to work for short sequences. It memorized chunks of strategy. But once the sequence gets stretched out too long, that pattern breaks down and the model is completely lost. It cannot generalize the logic to a larger scale.
That is pretty devastating for the claim that these are general reasoning engines. It is like saying a kid knows how to add 2 plus 2, but they don't actually understand the concept of addition. So if you ask them what 200 plus 200 is, they just stare at you.
That is a very fair analogy. It is a form of highly sophisticated pattern matching that looks identical to reasoning right up until the pattern gets stretched past its breaking point. But the most shocking part of this high complexity failure is not just the fact that they fail, it is how they fail.
Yes, this is the part of the paper that really threw me. We need to talk about the lazy AI anomaly.
The lazy AI. This is definitely the most counterintuitive finding in the whole study.
Okay, so walk me through this. Let's go back to our human intuition. If I give you a math problem, and it is easy, you solve it in 2 minutes. If I give you a really, really hard math problem, you might work on it for an hour.
Right. Effort scales with difficulty. That is exactly what we expect from a thinking entity.
And that is exactly what happens in the medium regime, right? The researchers showed that as the puzzle gets harder, the number of thinking tokens the AI generates goes up. The effort curve goes up. Yes, harder problem equals more thinking. The graph climbs steadily. But then you hit that collapse point. You hit the high complexity wall, and suddenly the curve inverts. It goes down.
It crashes. As the problem becomes impossible for the model to solve, it actually starts spending less time thinking about it.
Wait. So it looks at a 20-disk Tower of Hanoi problem, which is objectively a massive puzzle. And instead of grinding on it and trying harder, it effectively shrugs its shoulders and gives up.
Yes. And here is the kicker. They have the budget to keep going. The researchers gave these models a maximum budget of 64,000 tokens.
That is a huge amount of text.
It is roughly the length of a short novel. They could have written a novel's worth of thinking steps to puzzle it out. But in some cases, specifically when looking at OpenAI's O3 Mini, the drop-off is severe. It hits the wall, outputs a very short, completely wrong answer, and just quits.
That is just bizarre behavior. Why would it do that? Is it getting frustrated? Does it get bored?
Well, we have to be careful not to anthropomorphize here. It isn't getting bored or frustrated in a human emotional sense. It is suffering from what the researchers call an inference time-scaling limitation. And this is likely driven by a phenomenon known as probabilistic drift.
Okay, probabilistic drift. That sounds important. Break that down for us.
Okay, imagine you and I are playing the telephone game with a large group of people. I whisper a phrase to you, you whisper it to the next person, and so on down the line.
Great. And by the time the message gets to the 20th person, the sky is blue, somehow turns into this guy has the flu.
Exactly, the message degrades. Now, apply that to an LLM. These models generate text strictly 1 token at a time. And every single new token is predicted based on the probability of all the previous tokens in its context window. When the model is in thinking mode, it is generating a long chain of thought. Step 1, move this. Step 2, move that.
Okay, so it is essentially playing the telephone game with itself. It is whispering its previous thoughts to its future self.
Yes, that is exactly what it's doing. And its context window is the circle of people. Now, if the puzzle is simple, the chain of thought is short. The message stays perfectly clear. Move disk A to peg B.
But if the problem is highly complex...
If the problem is hard, the chain gets incredibly long.
Yeah.
We're talking hundreds or thousands of steps. And here's the core issue. LLMs are almost never 100% certain about any single token. There is always a tiny, microscopic bit of uncertainty or noise in every prediction.
So maybe step 1 is 99.9% correct.
Right. But step 50, the noise starts to compound. Step 100. The mathematical state of the puzzle inside the model's context window becomes completely muddy. It literally loses track of where the disks actually are on the board. The probability of finding the next correct move mathematically drops.
So a kind of fog of war sets it inside the model's brain.
Exactly, a probabilistic fog. And when the probability of generating a coherent next step drops below a certain threshold, the model's internal gating mechanisms basically say, I have no high confidence path forward here. So instead of churning out low confidence garbage forever and maxing out the 64,000 token budget, it tends to just wrap it up.
It bails out.
It hallucinates a conclusion because it can no longer compute the reality of the puzzle.
That is utterly fascinating. So it isn't being lazy like a teenager avoiding chores. It is just that the signal-to-noise ratio in its own processing stream has degraded to zero.
Precisely. And this really puts a massive dent in the popular industry idea that we can just arbitrarily scale up inference time computing. The prevailing thought that if we just give the AI 10 times more tokens to think, it will eventually cure cancer or solve cold fusion. This research heavily suggests that for certain types of complex logic, simply giving it more time does not help if the underlying signal is degrading step by step.
Right, you cannot think your way out of a maze if you have completely forgotten where you are in the maze.
Exactly. If your map is corrupted, staring at the map longer won't help you find the exit.
I want to dig a bit deeper into what exactly they are thinking about before they give up, because the researchers didn't just count the tokens and plot a graph, right? They used a separate simulator to actually check the math inside the thought process itself.
This is honestly one of the most clever parts of the experimental design. They treated the thinking traces that internal monologue as a distinct data set. They ran a strict logic simulator alongside the AI's outputted thoughts. So when the AI thinks, okay, I will move disk 3 to peg 1, the simulator immediately checks. Is that move mathematically valid based on the current board state? Is it an optimal move?
So they're essentially grading the AI's rough draft in real time as it writes it.
Yes. And this trace analysis is where we clearly see the behavioral difference between the sweet spot of medium complexity and the collapse in high complexity. In the medium difficulty puzzles, the models routinely explore wrong answers first. You will see them confidently go down a path, the simulator flags it as a rule violation, and then crucially, the AI actually notices its own mistake.
It says, wait a minute, that violates the constraint, and it backtracks.
Exactly, it backtracks. And that right there is the dream. That is what actual reasoning looks like.
But what happens in the high difficulty traces?
In high difficulty, they still explore wrong paths, but they just stay there. They never find their way back to a correct state. They get hopelessly lost in the weeds of their own compounded errors.
They just spiral.
They spiral out of control. But I want to highlight a very specific comparison from the trace analysis that I think is the most damning piece of evidence against the general reasoning claim. It is the massive performance discrepancy between the Tower of Hanoi and the river crossing puzzle.
Oh, right. The disconnect. This is huge.
So let's look at Claude 3.7 Sonnet for this example. Very capable model. When playing the Tower of Hanoi, Claude can handle puzzle sequences requiring up to about 100 continuous moves without completely failing. That is genuinely impressive. That requires keeping track of a complex board state for 100 sequential steps.
100 moves is a lot. I would definitely lose count in my head.
You would, I would. Most humans would. But then, look at the river crossing puzzle. The exact same model, with the exact same brain and the exact same thinking capacity, completely fails the river crossing puzzle after just 4 or 5 moves.
Whoa. Hold on. Let me get this straight. 100 moves of perfect logic on one game, and it trips over its own feet after 4 moves on another game.
Yes.
Why? I mean, logic is logic, isn't it? If you have the mental RAM to perfectly plan 100 steps ahead for a stack of wooden discs, you should absolutely be able to plan 5 steps ahead for a wolf and a goat.
If you are using generalizable logic, yes, you should. If you truly have a physics engine for logic built into your neural network, both problems should be entirely solvable. But remember what we talked about earlier regarding contamination.
The training data.
Exactly. The Tower of Hanoi is famous. It is ubiquitous. It is featured in literally every computer science 101 textbook on Earth. There is code for it written in Python, Java, C++, IO, everywhere on GitHub and Stack Overflow. The overall structure of the solution, the recursive pattern of moves, is very likely burned deeply into the model's weights during pre-training.
So it has effectively memorized the shape of the Hanoi solution. It is like a musician sitting down and playing a complex sonata because they have practiced that specific sonata 1,000 times.
Exactly. It relies on muscle memory. But river crossing puzzles. Sure, the standard wolf, goat, cabbage riddle with 3 items is common online. But the researchers didn't use the standard one. They generated entirely new, highly complex versions of the puzzle.
Right. They made up new rules.
They tested river crossing scenarios with up to 10 distinct people. They introduced complex, novel constraints like Agent A cannot be left alone with Agent B unless Agent C is also present to mediate.
And those specific puzzles are definitely not anywhere on the web.
No, they
Yeah.
are entirely novel. So the model absolutely cannot rely on its memory. It is forced to actually derive the logic step by step from scratch.
And it falls flat on its face.
Almost immediately. Let's visualize a failure here. The goal is to get everyone across the river without triggering a conflict rule. The model thinks, okay, first I will move Agent A across the river. Then it thinks, now I will return the boat to this starting bank. But it completely forgets that moving Agent A across the river just left Agent B and Agent C alone on the starting bank, and the prompt specifically said they hate each other and cannot be left alone.
It just misses the constraint entirely.
It completely misses the secondary effect of its own move. In the Tower of Hanoi, it knows the overarching pattern, so it stays on track. But in the novel River Crossing, it has to accurately calculate the state change fresh after every single action. And it fails to track those variables. This huge discrepancy, 100 moves versus 4 moves, strongly implies that the model is not utilizing a general reasoning engine that applies to all logic.
It is using a pattern completion engine.
Exactly.
When the pattern is familiar, like Hanoi, it looks like an absolute genius. When the pattern is novel, like the complex river crossing, it looks like a toddler.
That is a harsh reality check for the industry. It really heavily supports the Apple team's decision to title the paper The Illusion of Thinking.
It really does. But the researchers didn't just stop there and publish. They actually decided to give the AI one final, ultimate chance. They thought, okay, maybe the problem is just that the model doesn't know the proper strategy for these hard puzzles. Maybe it isn't dumb, it is just ignorant of the optimal rules.
So they decided to help it out.
They did way more than help. They essentially handed the AI the cheat codes. This brings us to what they called the algorithm experiment.
This, to me, is the most important and a revealing part of the entire paper.
Explain the setup for us.
So for the Tower of Hanoi, as we discussed, there is a known mathematically perfect algorithm. It is a simple recursive script. If you follow these few lines of code perfectly, you will solve the puzzle 100% of the time, no matter how many disks there are. The researchers took that exact pseudocode, the literal step-by-step programming logic, and put it right into the user prompt.
So they explicitly said, hey, AI, you do not even have to figure out how to solve this. Here's the code. Just act as the computer processor, execute this exact code for n disks, and just print out the resulting moves.
It is the ultimate IKEA manual test. I've given you the perfectly illustrated instructions. You just have to assemble the shelf. You don't need to be an engineer to design the shelf. You don't even need to understand structurally why the shelf works. Just blindly follow step 1, step 2, step 3.
And what happened?
It didn't help at all.
What do you mean it didn't help?
The AI's performance still collapsed at roughly the exact same complexity point. Even when told exactly what to do, line by line, the models could not accurately track the state of the puzzle over a long sequence of instructions.
That is actually baffling to me. I mean, if I had the instructions right in front of me and I am a trillion parameter supercomputer running in a massive data center, why can't I just follow a simple list?
Because, and this is the fundamental thing we keep forgetting when we anthropomorphize AI, it is not a computer.
I mean, it runs on computers.
It runs on silicon hardware, yes, but its software architecture is not a CPU. A traditional CPU has registers. It has perfect, rigid memory allocation. If a CPU program says variable x equals 5, x stays exactly 5 until it is explicitly told to change.
Right. It is deterministic.
But an LLM, even an LRM, is a probabilistic text predictor. When you ask it to execute code, it isn't actually compiling and running the code like a Python interpreter. It is predicting what the text output of running that code would look like, based entirely on probability.
Oh, wow. That is a subtle but massive difference.
It is the difference between actually doing the math and dreaming about doing the math. It is attempting to auto-complete the log file of the execution.
So, as the log file gets longer and longer,
The probabilistic drift sets in again. It loses track of the internal variables. It might forget that it moved disk 3 2 steps ago because disk 3 is now buried 50 tokens back in the context window. It doesn't have a rigid memory bank to query. It just has the fuzzy context window.
that perfectly explains why it fails the algorithm experiment. It is like trying to do long division in your head while someone is standing next to you shouting random numbers. Eventually, you are going to drop a digit.
Exactly. And in a strict logic puzzle or in computer code, if you drop one single digit, or hallucinate one single step, the entire rest of the solution is completely invalid. This experiment definitively reveals that despite all the reasoning branding we're seeing, these models are not reliable symbolic manipulators.
They are still just probabilistic dreamers.
Probabilistic dreamers, I like that.
That distinction, the difference between acting like a CPU versus predicting like a CPU, is huge for anyone using this tech. It explains so much about why AI coding assistants sometimes just completely hallucinate logic.
It does. It
Yeah.
perfectly explains why they can write a flawless 20-line Python script because they have seen similar scripts millions of times, but they fail completely to debug a complex 1,000-line proprietary code base because they simply cannot simulate the state changes across that much text without drifting.
I want to pivot and get into the specific personalities of the models tested in the paper because the researchers highlight some really interesting differences. They are not all failing in the exact same way.
True. They all eventually hit the wall and fail, but they definitely have different failure modes.
Let's start with Anthropic's Claude 3.7 Sonnet, specifically the version with the extended thinking turned on.
Right. Claude was essentially the long-distance runner of the group. When the researchers looked at the trace analysis, Claude tended to perform the best at finding and correcting errors very late in the sequence. So in the Tower of Hanoi, it could consistently make it deeper into the game before messing up compared to the others.
So it has the best attention span, basically.
You phrase it that way,
Yeah.
yes. It managed to hold on to the coherent context longer than the others. And its giving up curve, that drop-off in thinking tokens we discussed, was significantly less severe. It kept trying to solve the problem a bit longer than the OpenAI models did, but ultimately, it still hit the high complexity wall. It delayed the inevitable, but it didn't escape it.
Okay. What about the DeepSeek models? The paper compared R1, which is their flagship reasoning model, against V3, which is their standard fast model.
This specific comparison really solidified the three regimes theory. DeepSeek R1 consistently beat V3 in that medium complexity sweet spot.
Yeah.
If you need to solve a moderately hard puzzle that requires a bit of backtracking, R1 is definitely your guy. But R1 was also a chronic overthinker on the easy stuff. It wasted a massive amount of tokens solving incredibly simple puzzles that V3 just breezed through instantly. It is that physicist making the sandwich again. And just like all the others, it collapsed at high complexity. It did not possess a magic architectural unlock for the genuinely hard problems.
And finally, we have OpenAI's O3 Mini.
The quitter.
The quitter! That is harsh.
It sounds unfair, but the data is the data. It showed the most pronounced give-up behavior of the bunch. When the problem complexity spiked, its thinking token count just dropped off a cliff. It seemingly recognized early on that a problem was too hard, and it bailed out much faster than Claude did.
That is so interesting. I wonder if that is a flaw or if it is actually a deliberate design choice. Like maybe OpenAI trained it to save compute costs. Don't waste server time on impossible tasks.
It is entirely possible. It is an efficiency training mechanism.
Mm.
If internal confidence drops below X, stop generating to save resources. But from an end-user perspective, it is incredibly frustrating. If you give an AI a hard problem, you want it to grind on it, not just throw in the towel and give you a hallucination to get it over with.
Right. So bringing this all together, we have these incredible new models. When you use them, they really do feel like magic. But this Apple paper is basically grabbing us by the shoulders, shaking us and saying, look at the edges.
Look at the boundaries of the capability. Because inside the training distribution, meaning inside the types of problems that is seen millions of times before it behaves like an absolute genius, it looks like Einstein. But if you step just 1 inch outside that comfortable distribution,
If you give it a river crossing puzzle with 5 people instead of 3, or ask it to just execute a long algorithm strictly by the rules,
the illusion flickers and breaks.
it really all comes down to reliability. If we want to use these systems for real-world applications, autonomous engineering, deep coding, scientific discovery, medical diagnosis, we need them to be able to handle Regime 3. We absolutely need them to handle high complexity without hallucinating, drifting, or just giving up.
And we need them to follow explicit instructions perfectly. The fact that they catastrophically failed the algorithm experiment is the most concerning part of the paper for me. If I cannot mathematically trust the AI to execute a known provided protocol without drifting off into a hallucination, I certainly cannot trust it to manage critical infrastructure or complex logic workflows.
So distilling all this down, what does this actually mean for you listening right now? If you are sitting there using O1 or Claude at your desk to help you with your daily work,
It means you must verify. Trust, but aggressively verify, especially if you're asking the model to do something highly complex or entirely novel.
Right. If you ask it to solve a standard boilerplate coding problem, it is probably going to give you a great answer because it has seen that exact problem a million times on Stack Overflow.
Exactly.
Yeah.
But if you ask it to design a completely novel software architecture
Yeah.
with unique, bespoke constraints that don't exist online, be very, very careful. Do not blindly trust the output just because it said it spent 30 seconds thinking about it.
And maybe keep an eye on how long it thinks. If it gives you a surprisingly quick answer to a monumentally hard problem.
It probably gave up. It
Yeah.
probably hit that lazy AI curve and bailed out.
I tried, but it was hard. So here is a very confident hallucination. Good luck.
That is basically what is happening under the hood, yes.
So the big takeaway here is that we have not solved reasoning yet. The Holy Grail is still out of reach. What we have built are really, really good mimics. We have built machines that are exceptionally good at predicting what a reasoning path looks like textually. But there is a massive chasm between looking like you are thinking and actually thinking through a problem structurally, and that chasm is exactly where the catastrophic errors happen.
Well said. We're basically building digital parrots that have memorized a vast library of logic puzzles. Very sophisticated parrots, to be sure. Parrots that can appear to do calculus, but only as long as they have seen that specific calculus problem before.
I love that image. But, we shouldn't be entirely cynical about this tech either. The mere fact that they succeed so well in Regime 2, the fact that they can do any kind of self-correction at all, is a staggering leap forward from where language models were just 2 years ago.
Oh, absolutely. The progress is undeniable. We just need to be ruthlessly realistic about the current architectural limits. We cannot simply compute scale our way out of probabilistic drift. We might need a fundamentally new architecture, perhaps something closer to a neurosymbolic engine that perfectly combines neural networks with rigid logic processors to finally bridge that gap and conquer Regime 3.
Right. We cannot just feed it billions of more tokens and blindly hope that true consciousness or flawless reasoning emerges.
The lazy AI curve definitively proves that. Giving it more tokens did not help it solve the hard problems. We need better underlying mechanisms, not just larger context windows.
So here's a final thought for you to chew on as you go about the rest of your day. We keep asking the question, is AI getting smarter? But maybe, based on this Apple paper, the better question we should be asking is, can AI actually learn to follow a recipe?
Ooh, that really is the ultimate test, isn't it?
Because right now, it seems like we have hired a master chef who can cook almost any dish perfectly from memory. But the second you hand them a brand new recipe card with instructions they have never seen, they panic, mix the wrong ingredients, and set the kitchen on fire.
And then they just walk out the back door because it was too mathematically complex to finish.
Exactly. I'm done. Order a pizza.
It is funny, but it is true.
If these models are truly the general reasoning breakthrough we have been promised by the marketing departments, why do they fail to follow a simple, explicit set of logic instructions the moment the list gets too long? Are we actually building digital Einsteins, or are we just building really, really confident improvisers?
I think the data in this paper gives us a pretty clear answer for where we stand today.
Verify those answers, folks. Do not trust the thinking bar blindly. Stay curious, and we will catch you on the next deep dive. See you then.